9 is kind of tricky because of the setup. You don't have two objects pulling on this one object here. They're all suspended by this pulley system. But in the end, you're still finding the tension in two different cables or strings. And if you kind of take the pulleys out, you can start to see some similarities to the problems you've been doing. The angles are going to be in a little bit different place. So you really got to be careful with your sine and cosine values as you find components as well. We can add some helper lines and kind of put angles in here similar to what we've been doing so far with some of the crane problems. But I think it's kind of easier to go with what we've got and then be careful with how we set up our components. So I'm going to go ahead and add some angles, A and B. The first thing I want to set up is figuring out the measure of these two angles. So I'm going to use a tangent function in this case because I've got an opposite and an adjacent side. And it's not so much about the force vectors, it's more about the distance vectors. And those can be two different things. They can happen in the same setup. We can have different length measurements, that's a magnitude. And each, on top of that length, there can be a different tension or force in the string or cable, and that's a different magnitude. Vectors measuring something different, so that's okay. But we've got 10 over 24, so I'm going to set up a tangent. Tangent of A is 10 over 24. So to find angle A, I need to take an arc tangent of 10 over 24. Okay. For B, it's going to be a pretty similar situation, except it's 20 over 24. So for B, it's arc tangent 20 over 24. So I went ahead and put these in the calculator and got my angle measures. I'm going to go to 2 decimal places here. That's going to get us close enough. I would really recommend you keep these precise values as you go through the problem with the calculator. So angle A is 22.62 degrees, angle B is 39.81. Went ahead and circled those. It's not my final answer, but there's going to be a lot of things I've got to find throughout the problem, so I want to have them kind of easy to find again. All right, so we've got that. Now, something that's kind of misleading about this problem, since they both share this common length of 24, both strings, it's kind of tempting to assume that they both are going to pull upward with the same amount of force, but that's not the case because they're at different angles. And long story short, the more straight up and down you are, the more upward pull you're doing. The more at an angle you are, the more of your tension, more of your force is going off to the side and less is going up. So these are going to pull with different amounts of upward force. So the next piece I'm going to look at is that free body diagram. That's something you'll use quite a bit in physics. So I know that this weight is pulling down with 5,000 pounds. Right? Well, that means that my two y components have to pull up with that same amount. So y1 plus y2 is going to have to equal 5,000. And then my x vectors, or x components, are balancing each other out because it's not moving left or right. So these are equal. The next logical thing to do is figure out what your components are. So this is back to the beginning. I was talking about making sure that you stay relative to the angle when you set up your components, your sine and cosine values. So if I want to find out the horizontal component of this first tension vector, the x1, I'm going to be setting up a sine value. So sine of A is going to equal whatever x1 is over my tension. And I'm going to rearrange that for x1, so t1 times sine A. All right, your y1, and I'm just going to kind of skip steps because you've done this quite a bit at this point. You can always set up your ratios if you need to. Your y1, if it's going to go with this direction, all right, that's going to be relative to angle A, but it's going to be a cosine because it's an adjacent side. So T1 cosine A. And again, these are normally the other way around. Cosine is usually a horizontal direction. Sine is usually with the vertical. But because of the way the angle's working out, my horizontal component relative to the angle is opposite, so that's a sine value. The vertical component is adjacent to the angle, so that's going to be a cosine. All right, as far as my x2 and y2, the x2 side component is going to be opposite of angle B, so T2 sine angle B. And y2 is going to end up being T2 cosine angle B. Now I'm going to leave, I know I've got the actual angles figured out, but I'm going to go ahead and leave them that way just because it's less writing. It's easier to put an A than it is to write all those numbers. And at the end I can plug it in when I need to. Once you get all this stuff figured out, it's going to work like most of the other problems. I'm going to start with my x components and setting those equal. So I know that T1 sine A has to equal T2 sine B. And then I'm going to go ahead and work on this equation and then kind of put the two together. So y1 is T1 cosine A plus y2 T2 cosine B equals 5,000. And as usual, now I've got T1 and T2 in both equations, so I need to do some substitution or elimination if you're really of interest. Substitution seems to work well. So I'm going to solve for T1. That's going to be T2 sine B divided by sine A. So that's going to plug in over here for T1. So T2 sine B divided by sine A times cosine A plus T2 cosine B is 5,000. Just to make it a little bit easier to work with, I'm going to factor out this T2. When I do that, I've got sine B over sine A times cosine A plus cosine B. So I'm going to go ahead and put all this in the calculator. But what's going to happen is I'm going to take all of these values and get a number answer. It's going to be a small decimal. And then 5,000 will get divided by this to get T2. So here's the number answer to all of the combination of sine and cosine values. If you need to see all that worked out in detail, you can always check it out on the website, and I do have the full solution posted to this problem. So you can't see all the numbers and how they play out. But I've got a decimal for all of this now, so I'm going to take 5,000 and divide by that. And that's going to be tension 2. And I'm getting 2,169.44. I went ahead and gave it a couple decimal places. Honestly, I'm okay if you're within maybe 1 or 2 pounds here. I mean, out of a couple thousand, if you're a couple pounds off, you're pretty close. That's all going to really come down to the rounding that you did with these angles. So, you know, more decimal places you can carry through, the more precise your answer is going to be, as always. So that's the tension in the second row. So the tension in the first, we can just plug this in times sine B divided by sine A. After doing all that, I get 3611 point, let's call it 3. And just to kind of finalize a couple ideas here, these are our two tensions. The one that's got the more upward angle is going to be doing most of the lifting. So we were talking about earlier how they're not doing the same amount of upward force because this one is pulling more up. This one's pulling more kind of out that way. So a lot of your force is being kind of wasted that direction. But anyway, the first one is more upward, so it has more tension on it. And that's what you're seeing happening below. In 101, we've got a big boat being pulled by 2 smaller tugboats. And we're trying to figure out the tension in the cables that are pulling in each direction. Now, we're assuming that they are, if this is the direction it's moving, they're pulling at the same angle to that direction of motion. So we'll go ahead and say tension 1, tension 2. It really doesn't matter which one you call tension 1, tension 2. It'll all work out in the end. Part A, we're supposed to come up with a function, solve it for the angle that describes the tension in these cables. So I'm going to begin with the free body diagram. That's kind of the best place to start with physics problems like these. Sort of like the last one, you can't get so hung up on x is always equal and y is always sharing the load. In this case, in our x direction, that's where the pull's happening. That's where the resistance to motion's happening. In the y direction, they should be kind of balanced. So I'm going to go ahead and say y1 and y2, they're pulling against each other in these directions. It's just all about how we have it drawn out. Now the barge here is 6,000 pounds, so it doesn't want to move. It's pulling backwards with 6,000 pounds of force, which means the two tugboats have to pull together forward with 6,000 pounds of force, or actually more than that to get it to move. But we're going to keep it balanced here. Let's just assume that they're at that point right before it starts moving, that everything's sitting still. So let's go ahead and make some equations out of this. We know that y1 in this case equals y2, and that x1 plus x2 is going to equal 6,000. This function will be fairly general because I've got so many variables at this point, but the components, the y components, relative to the angle, your y components are going to be a sine value. So this is kind of back to the normal way it works out. Again, it's just relative to the angle. Sine of the angle would be y over t. So if I'm solving for y1, I'll set 1 up and then we can use it kind of as a model, hopefully. Sine of theta would equal y1 over t1. So if I want to solve for y1, it would be t1 sine theta. So that's t1 sine theta. y2 is going to end up being t2 sine theta again because relative to this angle theta, they're both the same angle. You've got y2 over t2. So at this point, if it's sine of the angle on both sides, and we know the angle is the same, sine value is going to be the same. So that decimal is going to work out to be exactly the same thing. This part can be divided out. Because whatever this angle is, that is a decimal number. So this is okay. We can divide this out. Which means T1 equals T2. And at that point, knowing that, I'm just going to get rid of the distinction of T1 and T2 and just call them T. It's going to actually make the process easier. Because it's the same angle, therefore it's the same tension in each boat. And we've proved that now. We've done a diagram, we've done our free body diagram, set of equations, and we've proved that has to be true. So let's look at the x components now. So relative to the angle, x1 is going to be a cosine ratio. So cosine of the angle will be x1 over t. So t times the cosine of that angle. On the bottom, it's going to be the exact same thing. It's cosine of this angle is x2 over t. So t cosine of the angle. And it's going to equal to 6,000. Smush, but that's what that is. All right, well now, you got t cosine theta twice, so I'm going to go ahead and condense that to 2t cosine theta. Equals 6,000. I'm going to divide the 2 off. So I get 3,000. And again, part A is asking me to solve for t. So to get t by itself, I'm going to divide by cosine. But you really want to simplify these as far as possible. If you're dividing by cosine, that's the same thing as multiplying by the secant value. Now in a calculator, we don't have a secant button, so you would have to do it this way. Now the next few parts of the problem, you can certainly go in your calculator and check your work. I don't think we need to spend too much time talking about how to plug in 10, 20, and so on in there. The trend you're going to see is that tension is increasing directly as the angle increases. All right, well I'm going to flip to a graph real quick. Because this is our secant graph. This is this equation graphed out. So really, first quadrant is the only thing we're going to be looking at practically because, let's take a second, I think that was part of the question at some point too. The domain has to be from 0 to 90. And we can talk about whether 0 or 90 are inclusive or not. 0, actually we probably, in practicality, you could never have a 0-degree angle because then the tugboats would be occupying the same space. I believe the book has it being okay, but that, I guess in theory, if one rope was slightly longer and they were, maybe one was in front of the other, you could make it happen. It's really just the physical part about it because would the boat move? Well, if somehow you could work it out with the tugboats were directly in a straight line with the boat, that would be really efficient for pulling the bigger barge here. So it's in theory possible. It would definitely move the boat. Well, let's think about what happens as the angle increases. Well, consider these y components. They are pulling opposed to one another. To give you a preview of something coming up, if you think about pulling a sled across the ground, the most efficient way to pull a sled would be to reach down to ground level and pull it, but it's not really practical. You have to reach really far down, so you're going to have the rope kind of be in an angle while you're pulling it behind you. It's kind of the same thing with the tugboats here. It's not really practical to have them right in line with each other, or they might bump into each other and that'd be problematic. So we need them to kind of be apart a little bit. That's the whole point of this angle, why it's there. But we really, from the math, and going back to the graph in a second, we want the boats to really be as close together as possible, so most of the effort's being done in the direction you want to go. Get ready to talk about work here in the next section. Work is the amount of effort that's getting something done, basically. So, in other words, these Y components are wasted effort. That's just the tugboats playing tug of war with each other and not really getting anything done as far as moving this barge forward. And you can probably imagine that the bigger this angle gets, if you kind of think about the direction the boats are going, they start spending more of their energy fighting each other than they do pulling this barge forward. If you ever went to 90 degrees, then the tugboats are completely playing tug of war with each other and not doing anything to pull this barge forward. So that's why 90 is really out of the question. The barge will no longer move if you make it to 90. And that's going to show up in your graph here. Because when you actually check out the graph here, we do have an asymptote at 90 degrees. Not in radians, but you would have an asymptote at 90 degrees because at that point you're no longer pulling the boat forward. So because there's so much more wasted energy, the bigger the angle gets, that's why you're going to start to see the tension needed, or the tension in the cable start to go up. All right, and it's going up steep and it's approaching an asymptote. So at some point, the tension will become infinite. So let's think about that practically again for a second. If these boats start pulling almost a 90-degree angle, again, they're just playing tug of war with each other. They're barely moving this barge forward. And they're just pulling with everything they can pull with. So without any practical limits of what a motor can do, I mean, there's no limit to how much tension you would have. Of course, there are practical limits. The motors can only do so much. The ropes can only carry so much. And they'll snap. But you would approach infinity in the tension in both cables as they get further apart. So that brings me to the part I made up on part E, which I think is a really important question to ask in this problem. So as the angle is getting closer to 90 degrees, the tension is approaching infinity. And we can think about it practically with the boats, we can think about it with our graph, but as your angle gets closer to 90, the tension in your cables is getting closer and closer to infinity. 102, I'm not going to actually give the answers here because you can look those up, but it's the same idea. Two people are pulling on a pail of water, or a bucket here, and they can't have their hands in the same place. There's always going to be some amount of angle between them. It's practical for two people to stand apart a little bit if you're trying to carry something, but not too far apart because we want to have most of our force going up. So kind of bridging between the last problem we did and what you're getting ready to do in the next section is the direction of your effort matters. You're trying to lift this bucket of water, gravity is going to pull down. We can't change that. So any effort we provide needs to be up. Now again, in practicality, some of your effort is going to be off to the side, but you want to have as little effort off to the sides as possible because that's really just kind of wasted effort. So we want as much effort as possible upward. We want these tension vectors to be as vertical as we can practically get without two people bumping into one another or hands crashing into each other or something like that. So just keep that in mind, that this is, any effort in these horizontal directions in this case is wasted. The only thing that matters is the upward force to lift this bucket. So something similar, if you've ever noticed about power lines, or maybe you have a clothesline, they're never exactly horizontal. There's always some amount of sag to those things. And that's sort of the same idea, because if we want it to, I mean, the cable has some weight, and those big power lines are pretty heavy, honestly. So gravity is going to pull it down. The only way we can overcome that is to pull it outward, okay? So that, now think about as these tension vectors are getting really close to being perpendicular to gravity. Gravity's pulling down, and they're really close to being perpendicular with that. Again, we need to pull up on the cable so it doesn't fall to the ground. But we also want to keep it stretched as much as possible. So With the bucket of water, we're trying to pull as much upward as possible. With a power line, you're trying to pull as outward as possible. I mean, you can't pull completely outward, but you want to go as much as you can. And it's the same issue. If we pulled, as far as an asymptote, it's kind of the same issue with this problem and the one with the tugboats. It would take an infinite amount of effort to get this thing horizontal, because there's always going to be some downward pull on the wire. Again, you can think of it just like you set up your diagram for the bucket of water. So if you're building something like that, you have to know the tensile strength, how much tension that cable can hold before it actually snaps, because we definitely don't want to put any more tension on that. So we kind of account for how much it's going to sag down based on how much tension we can put in the cable, and that leads to where they're spaced apart, how tall they are, so the power lines, of course, don't hit the ground or anything. But it can all be generalized back to the same idea as 101 and 102.